covalent. So let's start talking about single bonds. So what I would like you to do is draw out the electron configuration of chlorine twice. So you will need to pause. If you need to pause here, you need to get your workbooks, a mini whiteboard if you've got one at home. I want you to draw out the configuration of chlorine twice. And when you're done, you can come back to the video. So while we're here, you need to go to your notes. We're going past the little red box of textbook questions on 6.1, and we're going to go to the part that it says single covalent bonds. So a chlorine atom, it says, it says the intramolecular bond can also be referred to as, what have I said it a couple of times? It's going to be called covalent bonding. So that's that first gap. Then it says single covalent bonds. A chlorine atom, electron configuration 287, only needs to gain, having a look at our picture here, how many electrons? 1, to achieve a stable electron configuration. So our first line, a chlorine atom only needs to gain 1 electron to achieve a stable electron configuration. However, to achieve this octet configuration, when 2 chlorine atoms wish to form a molecule, they can't give an electron to the other. Yeah, so you can't have, sorry girls, you can't have 1 electron here go over to chlorine. Yes, that will satisfy this chlorine, it'll make it in a full octet, but this one will only have 6 valence electrons. And if you've only got 6 valence electrons, you're not happy. So they cannot donate, hence when they are close enough, 1 unpaired electron from each atom is actually going to be drawn into the region between them, and the result is that you end up with something that looks a little bit like this. Okay, so you can see that they come together and they have this little region in the middle there where they're going to share. Oh, the covalent ones are so happy because they love to share electrons. The ions are always like, the cations are always very giving. They're giving away their electrons. The anions are like, yeah, I'm greedy. I want to take in your electrons. But the covalent substances, they like to share their electrons. So as they're sharing their electrons, we end up with something that looks a bit like this. Now, I don't really like this diagram on the right here because it doesn't show you, sorry girls, it doesn't show you where the electrons belong to. So on your notes, can you colour in the fact that 7 of the electrons here are going to come from this green chlorine atom? You can highlight them, and then on the other side here, I'll just show you how you can highlight, yeah? You could colour in all of these and say those 7 electrons are coming from this chlorine atom. So what you end up here is 2 different types of diagrams. The first one on the left here is showing the shells, and you can see that there's this shared pair of electrons in the middle here. And this one on the right is showing you an electron dot diagram. It's a little bit easier to draw than one of these, and I'm going to give you some drawing practice in just a minute on how to draw them, and then we should be fine. So we'll just finish off these notes. It says underneath this picture, it says each chlorine atom now has access to both electrons. So if you were this chlorine atom, the yellow one on the left here, you can count around and go 1, 2, 3, 4, 5, 6, 7, 8. It has access to 8. The green one on this side, yeah, it has 1, 2, 3, 4, 5, 6, 7, 8 also. So because they're sharing, they both get a stable octet. So the electrons will spend a large amount of time between both nuclei, but they will spend some time revolving around the other one. So what will happen is this electron that came from the green one, at some stages, you'll even find it zooming around this side of the chlorine. Same with this electron that came from the yellow one. Sometimes it'll zoom around outside here. Okay, so this is called a diatomic. So we've got this. Each chlorine atom now has access to both electrons. The electrons will spend a large amount of time between the both nuclei, but will still spend some time revolving around either nuclei. A diatomic molecule has been formed. So this is how we spell it, diatomic, meaning 2 atoms. A diatomic molecule has resulted as a consequence of each chlorine atom's outer shell electrons being shared. Okay, because they're sharing it, we're forming this diatomic molecule. We describe the molecules as discrete because they are separate, distinct molecules made up of a definite number of atoms. Now, what we do is we write this as Cl2. Makes sense. We don't just have one chlorine, we've got two chlorines, and together they form Cl2. So what kind of attraction have we got here? We've got a really strong electrostatic attraction. So now we have a strong electrostatic attraction. Okay, strong electrostatic attraction. So this is the second paragraph. So the strong electrostatic force of attraction arises from the sharing of electrons in the outermost or valence shells of the atoms. It operates between the negatively charged electrons that are being shared and the positively charged nuclei that share them. The electrostatic force is being described, the electrostatic force of attraction that holds the atoms together in the molecule is termed covalent bonding. It is also described as intramolecular bonding since it operates inside the molecule. So here is the whole molecule. The bond is in here, so that's what makes it intramolecular bonding. It requires a huge amount of energy to split these two atoms apart. Hence, covalent bonding is very, very strong. Yeah, so this is one of our strongest forms of bonding. This is pretty much the strongest form of bonding, is covalent bonding. We'll look at the strength of different types of covalent bonds, but this is definitely super, super strong. So now what we're going to do is a little bit of practice on how you can do this. So you remember when I said when we draw the electron configuration, I wanted you to draw them around? Now, this is where it comes into play. So to begin with, I know what my molecule is. It's been told that it's H2. So I'm going to draw both hydrogens. Okay, I'm going to draw both hydrogens. How many electrons do they have in their outer shell? They have one each. I'm going to draw them with different symbols just so that we can see there. Now, how many does hydrogen need to complete its octet? It's going to need 2 because we're talking about the inner shell here. So what we can do is we can draw them again, and you end up with H, nice big circle, H on top of it. Here's the other one, and they're going to share both. And we can check that my molecule works by counting around. So this yellow hydrogen here has got access to this electron. That makes it happy because it has 2. Then we can see that this hydrogen over here, the green one, has access to both electrons as well. So it's got access to 2. So it's a happy molecule. And this is another way of showing it. You can draw it like that. If you were to draw the electron dot diagram, it would just look like this. So circles and crosses are a really good way to show which atom those electrons are coming from. So you can have a go of fluorine on your own. So you can pause and then restart. And we're back. So this time I'm going to draw fluorine. I'm going to know that fluorine on the periodic table has got 7 valence electrons, but it's got an inner shell. So I'm just going to draw its complete electron configurations. Hopefully I can fit these in. Yeah, so this one can have this. 1, 2, 3, 4, 5, 6, 7. Yeah, and over here we've got 1, 2, 3, 4, 5, 6, 7. I've got circles here. Yeah, now those 2 in the middle are going to be drawn together. They're going to share them, and you're going to end up with something that looks a bit like this. Let's try again. So give it a pause. Try and do them. This time I'm going to draw them straight away together. Okay, welcome back. So hydrogen. I know that hydrogen has got 1 outer shell electron. Okay, actually I'm going to make it the circle because I find crosses easier to draw. Chlorine has got 3 shells. 1, 2, 3. So that one's right there. I'm not going to draw my inner shell electrons just to save me a bit of time, but you can if you need to. And it has 7 on the outside. 1, 2, 3, 4, 5, 6, 7. And you end up with something that looks a bit like this. Good. This one's a bit trickier. So give it a pause, think about it. We've got 1 carbon and 4 hydrogens. Okay. Now you're back. You might want to think about carbon. So carbon has got 6 electrons. So it's going to have 2 in its inner shell, and then it's going to have 4 around here. And this is where you're going to see my magic happen. So this time I'm going to use a different color to show the other elements, just because it's going to make it a bit easier for you. You can do that too. So you can either do crosses and circles, or you can use a different color to represent them. So I'm going to put 1 hydrogen up here, because that hydrogen is going to share 1 electron. So that's going to make the hydrogen happy because it's got 2 in its valence shell. At the moment, the carbon only has 5, so it's not really happy. So I'm going to put another hydrogen down here. Yeah, it's going to have 2 in its outer shell, so it's going to be happy. Another hydrogen down here. Another hydrogen over here. Okay, now we can count just to double check. It's always a good idea to double check. How many does the carbon have in its outer shell? 1, 2, 3, 4, 5, 6, 7, 8. Carbon is happy. It has a full octet, a full 8. The hydrogen is happy because each one of those has 2, and that is its complete shell. And so what we end up with is a molecule that looks a bit like this. Now, if you were to do that as an electron dot diagram, you would end up with something that looks a bit like this. So there's another way of drawing it too. The last one we're going to do is water. So my advice is always leave your hydrogens to last. Okay, so have a pause, have a try, and then come back. Welcome back. So I'm going to start with oxygen. I'm going to draw oxygen out here. Oxygen has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, and you see why by drawing them around, what I've ended up with is 2 electrons that are kind of sitting out there on the top, so on the left-hand side and on the bottom. And then I can go, okay, how many does the hydrogen have? Because I've drawn lots of hydrogens. I'm going to draw that hydrogen in there. It's now happy. It's got a full outer shell. I'm going to draw the other hydrogen over here. It's now happy. It's got a full outer shell. Let's just check how many outer shell electrons oxygen has. 1, 2, 3, 4, 5, 6, 7, 8. Happiness. Okay, so that is how you draw single bonds and electron dot diagrams. If you were to draw that as a simple version, you can go 1, 2, 3. I'm only doing that. I'm cheating because I've already drawn it a couple of times. Then we've got this here. Now it doesn't matter where the hydrogens are. They could be up the top, down the bottom. They could be on either side. Whatever you want. Now we will talk about the shape of molecules and the shape of water in particular, but for now that's all you need to do. Good.